All right, let's talk about something that can make your AI search feel, well, a little fragile, a little unpredictable. It's a really subtle issue, but it has a huge impact. And it all comes down to the hidden geometry of your data. The cool part is, we're going to show you not only how to see it, but how to fix it.
You've probably been there, right? You build a retrieval system, it seems to be working, but something just feels brittle. You get this nagging feeling that the results just aren't as solid as they should be.
And these are the classic signs. You change one tiny word in your search query and the entire ranking just flips on its head. Or you look at your similarity scores and they're all kind of bunched up together, not really telling you much. And then there are those weird hub items that seem to be neighbors with everything. Yeah, that's not just bad luck. It's a sign of a much deeper structural problem. So what's the diagnosis for this? Well, you can think of it as a lopsided space. Now, that's my term, but it has a real technical name, and once you understand it, everything else just kind of clicks into place. That technical term is anisotropy, and the core idea is actually pretty simple. It just means your space has developed a kind of directional bias. So instead of all your information being spread out nice and evenly, it gets squished into just a few super highways of meaning. Here's a fantastic way to think about it. Anisotropy gives your data a grain, just like a piece of wood. It's super easy to move along the grain, but trying to go across it is really tough. And that means certain types of similarities get way overrepresented, while other, totally valid ones get ignored. Visually, here's what's going on. A healthy, balanced vector space should kind of look like a sphere, right? All the data points spread out evenly. But in anisotropic space, it gets stretched and warped into this long, thin cigar shape, where almost all the action is happening along one single line. So let's break it down. In a healthy isotropic space, that's the goal. Variance is spread out, the scores are actually meaningful, and your search is stable. But in an unhealthy and isotropic space, variance gets jammed into a few directions. The scores all clump together, and your search becomes totally brittle. What we want to do is get back to that healthy state over on the left. So how in the world does this even happen? Well, it usually comes from the training process, especially in what's called contrastive learning. During training, the model is told, hey, these two things are similar, pull them closer. These two are different, push them apart. The problem is something called false negatives. That's when the model gets told that two very similar items, like two sentences that are almost perfect paraphrases, are actually negatives and should be pushed apart. Now, imagine that mistake happening thousands and thousands of times. It literally warps the entire space and creates that dominant green we were talking about. Okay, so how can you tell if this is happening in your own systems? The good news is you don't have to guess. There are a few really simple checks you can run. I like to call these vibe checks, and they're super easy. First, just calculate the average of all your vectors. Has it drifted way off from the 0 point? That's a sign. Second, plot a histogram of your similarity scores. Is it just one big narrow spike? That's another sign. And third, are you seeing the same few hub items popping up in everyone's search results? If you're nodding along to these, yeah, those are all red flags for anisotropy. Now, if you want a more definitive test, the PCA scree plot is your best friend. This chart basically shows you where all the variance in your data is hiding. And if you see this pattern, one giant bar at the beginning, followed by a massive drop-off, that's it. That's the smoking gun. It's a clear visual confirmation that one single direction is totally dominating your entire space. Okay, so we've diagnosed the problem. Now for the fun part, the treatment plan. We can actually apply some really simple post-processing geometric fixes that clean this whole mess up and bring some balance back to our space. The very first and simplest treatment is called mean centering. All you do is calculate the average of all your embedding vectors, and then you just subtract that average from every single vector in your dataset. That's it. And what it does is it pulls that entire cloud of data points back so it's centered perfectly on the origin again. Honestly, the best way to think about this is like hitting the Terra button on a digital scale. You're not actually changing the weight of anything you put on it later. You're just resetting the baseline to 0 so all your future measurements are accurate. That's all mean centering is. It's a simple but really powerful re-anchoring of your whole space. All right, the next treatment is a little more targeted. It's called principal component removal, or PC removal. This method uses PCA to find that one dominant direction, that loudest signal we saw on the scree plot, and it surgically removes its influence from every single vector. A great analogy here is audio cleanup. PC removal is like finding a loud, constant background hum in a recording and just muting that one frequency. You don't mess with the rest of the music, you just take out that single overpowering noise so you can finally hear all the subtle details underneath. So if we go back to our visual metaphor, PC removal is what takes your data's shape from that long, stretched-out cigar and collapses it into more of a flat pancake. By getting rid of that one dominant direction, you let all the other, more subtle dimensions of meaning finally shine through. Now, it's really important to distinguish PC removal from a related, but much more aggressive technique called whitening. PC removal is like a targeted trim. You're just turning down the one or two loudest instruments in the band. Whitening, on the other hand, is a full rebalance. It's like an audio engineer adjusting every single frequency on the soundboard. For most cases, PC removal is a much simpler and, frankly, safer place to start. Okay, let's pull all of this together into a practical toolkit. What should you actually do with all this information? So you might be asking yourself, wait a minute, if these problems exist, have I been doing it wrong this whole time by just using embedding straight out of the box? And the answer is a definite no, not at all. Using embeddings as is the standard baseline, and a lot of the time, it's perfectly fine. The best way to think of these techniques is as optional geometry boosters. You don't need to use them unless you're actually seeing the symptoms we talked about. They're a tool in your toolkit, not a mandatory step. So if you decide you do need that boost, here's a safe, minimal recipe to get you started. First, mean center your entire collection of vectors. Second, gently shrink. And notice I said shrink, not completely remove, the influence of the top 1 to 3 principal components. Third, L2 normalize, which is just a fancy way of saying rescale all your vectors so they have the same length. And finally, and this is absolutely the most crucial part, you have to be consistent. Whatever you do to your stored data, you have to apply the exact same transformation to your queries. And that kind of leaves us with a final, bigger thought. We focused on geometry today, but really, this whole thing is about bias. Anisotropy is just a form of geometric bias that gets learned during training. And it forces us to ask a much deeper question. What other hidden biases, geometric or otherwise, are shaping the way our AI models see the world?